Hi everyone, here are your notes for section 6.4, which is general approach to factoring. So pretty much section 6.4 is a summative section of everything that we did in section 1, section 2, and section 3. So we're just kind of putting it all together to make sure that we can factor almost most, not all, because not all polynomials are factorable, but most polynomials. Okay, so there's nothing brand new that we're going to be learning here. Again, we're just kind of putting it all together into one lesson so that when we get into section 6.5, we then can get into how do we solve polynomial equations by factoring. Okay, so factoring a polynomial, here are the steps. Again, I'm just going to read through them. I'm going to assume that you're going to pause this video and just write down whatever it is that you need to write down. Step 1. Always look to see if you can factor out a common factor. That should be your first go-to. Do you have a GCF that you can factor out? If you do, factor it out. If you don't, then skip on to step 2. Step 2, if the polynomial is a binomial, meaning it has two terms, check to see if it's the difference of squares, the difference of cubes, or a sum of cubes. If the polynomial is neither of those, then you may only be able to just factor out a GCF. If the polynomial has more than 3 terms, so it has 4, or I don't know if we would ever get to ones that have 5, so probably just more, try factoring by grouping. And then step 3, check the factored form by multiplying. Now the factoring by grouping in step 2, you may group the first 2 together and the last 2 together, or what we got into in section 6.3 on a few of them. Remember, we were grouping a chunk of 3 together because they probably were perfect square trinomials, which then would give us a difference of squares. So kind of if you're looking at a group of 4 and that last term is a perfect square, or the first term is a perfect square, then you might want to try to factor by grouping of 3 to make a trinomial. That might be a perfect square trinomial. Okay, so here we go. We're just going to go through a whole bunch of examples to make sure that we can factor them. So step 1 always says factor out a GCF. In this case, I can factor out a 9, which leaves me with p plus 5. When I look at the remaining binomial that's there, I'm going to ask myself, is it a difference of squares? Definitely not a difference because there's a plus there. Is it a sum of cubes? Nope. P and 5 are not perfect cubes. So I am done. Always check your work to make sure that it multiplies back to the original, which in this case it does. Simple as that. B, 8m squared p plus 4mp. What's the GCF? I can take out a 4, I can take out an m, I can take out a p, and when I do that, I'm left with 2m plus, this is always going to be a 1. Some of you guys were losing points on past problems. If your GCF is the term, you need to have something there, so you need to have a 1 there so that you have something to distribute it to. Then if I look at the remaining polynomial, inside my parenthesis, 2m plus 1, can't be factored further, so I am done. Check it. That gets me 8m squared p plus 4m, so I know I did it right. C, I have 5x times the quantity a plus b minus y times the quantity a plus b. I see quantities of a plus b in both, so that's going to be your GCF. So if I take out an a plus b from the first chunk, I'm left with a 5x. If I take out an a plus b from the second chunk, I'm left with just a minus y. Now when I look at each of these individually, I can't simplify that or factor that any further, and I can't factor that any further. There's no GCF in this that I can take out, so now I am all done. Okay? Alright, looking at A, I thought it was going to be D, but now we're going to A. So factor each binomial if possible. So now I have some squareds happening. I see a subtracting. So my first gut instinct is to think I'm doing a difference of squares. 64 and 9 are both perfect squares. I cannot take out a GCF. The square root of 64 is 8. The square root of m squared is m. The square root of 9 is 3. And the square root of n squared is n, and then I'm just going to make these a plus and a minus. So remember, your difference of squares are going to have opposite in signs to eliminate that middle term. Again, always check it. 64m squared. I have a negative 24, positive 24. Those would cancel, and a negative 9n squared. Perfect. All right, 8p to the third minus 27. I see a to the third power, so my first thought is, probably going to be a sum or a difference of cubes. In this case, it's a difference. 8 and 27 are both perfect cubes. The cube root of 8 is 2. Cube root of p to the third is p, minus the cube root of 27, which is 3. So that gets you your first binomial. Then do you remember the rule for the second half? So we square this term right here, which would get me to 4p squared. If this sign right here is a minus, then my next sign over here is going to be a plus. To get the middle term, we multiply these together, which is going to be 6p. So 6p, and then to get my last term, I square the 3, or negative 3. But anytime you square anything, it's going to be a positive, so plus 9. And there would be your answer. Okay. If you were to distribute all of that out, you would have terms canceling out, and then you would be left with just 8p to the third minus 27. 100m to the third plus 1. Again, my first thought is, I see an exponent of 3, so do I have perfect cubes? Well, 100 is 10 squared, so that's not a perfect cube. 1 is a perfect cube. I can't take out a GCF to make this make it into something different that would make it into a perfect cube. So because this is not a perfect cube, because 1,000, that would be a perfect cube. That would be 10 to the third power. This one is actually prime. So remember, we write the word prime when it's not factorable. And what does prime mean? Prime means that you only have something times 1, so itself times 1. So really my only factor form would be that times 1, so that's what makes it prime. All right, 25m squared plus 121. I have perfect square here. 25m squared, square root it would be 5m. 121 is a perfect square, so that square root it would be 11, but this is not a difference of squares, so it's not going to be factorable. So here is another scenario where we would have a prime polynomial, so it's not factorable. Okay, so now we're going to go to trinomials. P squared plus 10p plus 25. Again, if we just use good old rainbow method, 1 times 25, factors of 25, that get you to 10, would be 5 and 5. Put it over 1. Because my factors are the same, this is going to be a perfect square, perfect square trinomial. Remember, your denominator goes with the numerator, so p plus 5 times p plus 5, which is the same as p plus 5 squared. That's why I don't really remember the rule for perfect square trinomials. You can, because the square root of p squared would be p. The square root of 25 is 5. 5 times p times 2 is 10p, which is your middle term. So that's how we could check it too, which is what you did in section 6.3. Here we have 49 and 9. So we could check to see if we have a perfect square trinomial, since I do have a perfect square here and a perfect square here. The square root of 49 is 7, and then the z, and then the square root of 9 is 3. So if I multiply those together and then double it, do we get 42z? Yep. So this is a perfect square trinomial. So I could just go right to 7z minus 3 squared. Or I could go the long way and do 49 times 9, which is 441, and then find factors of 441 that get you to 42. So it looks like probably 441, and 21. Yeah, 21 and 21. Both need to be negative. Put them over 49. So reducing that, take out 7, so it'd be negative 3 over 7, negative 3 over 7, which would get us the 7z minus 3 twice, right? Okay, here we have a -6, not a perfect square, so probably not a perfect square trinomial, so just factor it as usual. So 1 times -6 is -6. Factors of -6 to get you to -5 would be -1 and 6, right? Be careful. You might think -3 and -2 get you to -5, but those multiply to a +6. I need it to be a -6, which means I need to have one positive, one negative. So putting those over 1, y goes with the denominator, gets me 1y minus 6, 1y plus 1. Again, always multiply these back out to make sure you're doing it right, especially when you're taking a quiz or a test. 72 is not a perfect square, so I don't have a perfect square trinomial, so factor as normal, so 72, right? 1 times 72 is 72. Factors of 72, that get us to 18. Let's see, 72 and 6, so 6 and 12 adds up to 18. Put them over 1. R goes with the denominator, so 1r plus 6, r plus 12. Again, multiply it out to make sure it works. Here we have 2k squared minus k minus 6. My C2 and a 6, so my thought is maybe there's a GCF to factor out, but the middle term's a 1, so there is no GCF to factor out. So now I'm just going to do 2 times -6, which is -12. Factors of -12 that get me to -1, well, that'd be -4 and 3. Put them over 2, reduce, 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 reduce. -2 over 1, 3 over 2. Put the k with the denominator. So k minus 2, 2k plus 3 would be your final answers there. Again, always multiply it out to check to make sure it works. 28, 6, and 10, so 28z squared plus 6z minus 10. Again, I see a bunch of even numbers, so I'm going to take out a 2 by factoring it out. So that gets me 14z squared plus 3z minus 5. Now factor what's left over. 14 times 5, or -5, is -70. Factors of -70 that get us to 3, positive 3, is going to be 10 and -7. Put them over my leading coefficient of 14. Reduce 10 over 14, taking out 2 is 5 over 7. Taking out 7 in the next fraction gets us 1/2, -1/2. Attach the z to the denominator. So now we've got 7z plus 5 and 2z minus 1. Bring down that original GCF that you factored out in the beginning. Okay, hopefully these all seem familiar to you and are not brand new concepts. Okay, so now let's jump into four terms. So polynomial 4 terms. Alright, so my first gut instinct is to try to factor this by grouping of groupings of 2. So I'm going to group the first 2 together and the last 2 together. I can take out a y squared from the first, which leaves me with x minus y. I can take out an x squared from the last 2, which would get me x minus y, which is good because this is the same as this. So now that's your GCF. So I'm going to take that out, x minus y, which leaves me with a y squared plus, that was a positive x squared that we took out. So now I'm going to look at what's remaining. This x minus y, I can't factor that any further. But this looks interesting because I do have squares, but do I have a difference of squares? No, I have a sum of squares. So I cannot factor that any further. That's my final answer. Here again, we have 10 terms. I've got some large numbers, so I'm going to think, can I take out a GCF from everything? Nope, there's nothing I can take out of 24 and 45 and 9, so I'm going to group first by 2's. So I'm going to group the first 2 together and then the last 2 together. So I can take out, looks like a 4 and a k squared, which leaves me with 5k plus 1. Don't forget that plus 1. Oops. Here, this is a negative number, so I'm going to take out a -9, which leaves me with 5k plus 1, which is good because this and this are the same, which is going to be your GCF. So if I take that out, what am I left with? Well, I'm left with a 4k squared, and I'm left with a minus 9. Now look at what's left over. Can't take that any further, but look here. There we do have a difference of squares because 4 and 9 are both perfect squares. So that's going to factor to 2k plus 3, 2k minus 3, and then bring down your original 5k plus 1. And there will be your final answer. Okay, so keep on going as far as you can. All right, so now here I have a 4a squared plus a 4a plus 1 minus a b squared. Now this one looks interesting to me right away because look here, I have a minus b squared. Here I have a 4a squared. Those are both perfect squares, and specifically this one is a minus b squared, which is kind of telling me that these three up here probably would factor to a perfect square trinomial. So let's go ahead and do that. So let's just group it by grouping the first three together and go from there. So if I group the first three terms together and factor that, 4 times 1 is 4. Factors of 4 that get you to 4 are 2 and 2. Put them over 4. Gets you 1/2, 1/2. Attach your a to the denominator. So that gets us a 2a plus 1 squared. When I factor that, because it's a perfect square trinomial, bring down your minus b squared. Now you have a difference of squares. Well, remember with your difference of squares, you're going to have two sets of parentheses. You're going to have a plus, you're going to have a minus. I should probably move that plus over a little bit. Plus and a minus. What's the second half? That's the easy part. That's just b, because the square root of b squared is b. When you square root your first term, cancels out this square right here. So then you're just left with 2a plus 1 and 2a plus 1. So we have 2a plus 1 plus b times 2a plus 1 minus b. Difference of squares.